Hi, and welcome to the Simulation Step-Up series. My name is Ramesh Lakshmipathy. I'm a Senior Technical Sales Specialist with Dassault Systems SOLIDWORKS Corporation. Now in this presentation, we'll review part 1 of the results capabilities in SOLIDWORKS simulation and also learn some tips and techniques as to how these results can be used to not only understand the performance, but also make good design decisions. So let's get started. The agenda for this presentation is pretty straightforward. We'll start by looking at some system level and default options that can be set upfront to reflect on results plots in any model and any analysis type. We'll then take a look at the available results type. Then we'll take a detailed look at edit definition, chart options, and settings for a result plot that can be used to further customize the plot as necessary. Next, we'll look at ways of manipulating a results plot for visualization and making the most sense out of the results. And finally, we'll take a look at some results query options to get numerical or engineering data. So what does an analyst versus a designer engineer look for in a result? So in this slide are some general thoughts on viewing results in SOLIDWORKS simulation. While a more traditional analyst focuses on data such as stress, displacement, nodal errors, a designer or design engineer needs to focus more on the story or the performance suggested by the data. Bottom line is the difference is subtle but important. So for an analyst, the results are the end. For the designer, the results are a means to an end. The first place to start considering the results viewing options available is the SOLIDWORKS Simulation System options, which is accessible from the Simulation drop-down menu as shown here. Now these options will immediately affect all the studies in the current open document as well as the studies in other documents when they're open later on. So let's go ahead and review some of the system options. The results in high precision setting should be only used after understanding this better. This is actually a post-processing option, which means it does not affect the precision of the results. Rather, it allows you to display up to 16 digits when reviewing the results, but the results will have already been calculated. So make sure that you take care in listing results with anything more than a few significant digits though. There's a general tendency to give more credit than is due to analysis results with lots of decimal places since they look more accurate. The show yield strength marker turns on or off the red arrow on the color chart indicating where the yield strength of the material falls on the von Mises stress plots. Now this can be really handy, but it's only available if the yield strength is specified for the selected material and you are actually viewing a single material model. Next, the option for displaying the local quantum system triad should always be turned on. If you choose a stress or displacement quantity that are quantum system dependent, such as directional stresses or displacements, the XYZ direction is dependent upon the reference geometry selected. You also have the option to change the color chart background as well. If for some reason your results would look more professional with a different background, you can choose from the standard palette. If you deselect this checkbox, your color chart background is going to be transparent. And finally, you can change the font in your results plot to any true type font installed on your system. This can be very important for some reports and plots generated for a more professional look. Now, in the default options tab under results, there are several settings like default solver type, results folder setting, etc. Now, these settings again apply to all the studies created after a change for all the documents, not just the one that is open. So let's go ahead and discuss a little bit about on the option to view the intermediate results during a nonlinear analysis. So checking this box automatically displays real-time deformation of the model during a nonlinear analysis run as shown in this particular video. So this allows for making decisions to either stop the simulation and making adjustments to the inputs as necessary. Notice that there is also a dynamic on and off option available in the solver dialog box that can actually be unchecked so that we can turn off the dynamic update if it's not necessary. Now, under the plot settings, you can select to display the location of the min and max value annotation on results plots. You can also select the fringe and the boundary options under settings. Typically, a lot of users like you and me like the discrete fringe option as it clearly shows the color bands much better and helps to identify any discontinuity in the results very easily. The boundary options typically can be left as the default model option. Now, for the deformed shape options, it makes sense to select the true scale for any analysis having nonlinearity such as contacts and/or large displacements. So the default plot settings are pretty straightforward, but different people like to have the charts look differently. So let's take a look at some of the color chart options. An important setting is the number format. The floating format is the default and makes most sense to use unless the numerical data from the analysis are large enough to consider the scientific format setting. An example would be looking at fatigue life plots or looking at stress results in Newton per meter squared. Now, as stated in the previous slide, it is not recommended that you get carried away with the displayed decimal places on your plots. For stress plots, I would often display no decimal places to highlight the approximate nature of the results. For displacements, you may need to decide what number of decimal places best expresses the data. The colored options are self-explanatory and easy to use. We'll discuss the yield strength marker checkbox in detail later on in this particular presentation. And lastly, you can specify a set of default plots for each study type, and they will be created automatically in the feature tree as soon as the simulation study runs to completion. I usually want to see one means the stress, max principal stress, resultant displacement, and equivalent strain for all the projects I work on. Your choices might actually vary. Here is a model in SOLIDWORKS that I would like to use to illustrate the system and the default simulation options. Now, in my simulation work environment, under system options, pretty much the default installation settings are used. So for example, the color chart background color, that checkbox is left unchecked. So that way my chart legends are going to have a transparent background. Under the default options, under the plot settings, I have the show min and max annotation boxes checked. I'm using the fringe discrete option for all the results plots. And also for the deformed shape options, I have set the true scale factor for any studies having contacts or large displacements. And for all of the studies, the setting is automatic. Under the color chart number format, I have the floating option selected with the number of decimal places set to 3. And also I have the checkbox for specify color for values above yield stress also set, and that's actually a dark gray color. It's a good practice to set these options up front so that it minimizes the number of changes you otherwise might have to make on a particular results plot. So I'm just going to go ahead and create a quick stress plot and simply choose the type of stress as one means stress and click OK. And you can see that all the settings are reflected here immediately, and I have a plot now as desired. Now this slide lists all the results types available for color display in a static stress analysis. The plot types available vary depending upon the study type. Note that the ones highlighted in red require a reference coordinate system as described earlier. If you have never scanned through the options, now is a good time to familiarize yourself with the data that might lead you to make better design decisions. Let's talk a little bit about the design inside plot. Now this plot is what's called a useful geometry or volume utilization plot. It tells you what portions of the model are working the hardest to support the loads and restraints you have defined. The transparent areas carry little or no load, and the blue areas carry bulk of the load. In summary, a design inside plot shows the regions of the model that carry the most loads in an efficient manner. Some users may recognize this plot as a load path plot. You can use this information to redesign the model and reduce the model's material. One technique that most designers, engineers, or even analysts use is to look at the strain energy density plot. This technique is applied to the optimization of a machine frame, as shown here. The part is designed with the maximum design envelope possible and solved. A review of the strain energy density plot, which is shown furthest right here, shows the most useful geometry for this loading. Now, this may seem intuitive based on the stress results, but this is not always the case. So when the design is changed based on the useful geometry indicated by the strain energy density plot, the frame volume can be reduced significantly with only minor changes in the stress distribution. A closer look at the bearing bore that looked like the area of controlling stress shows that the stress of interest and total stiffness changed only minimally, but a 20% improvement in weight was actually realized. So similar improvements may be possible in your designs if you explore them using this additional piece of data. Next, the fatigue check plot alerts you if certain regions of your model are likely to fail due to repetitive loading and unloading over an infinite time. This plot is based on a single constant amplitude fatigue event with a fully reversible or zero-based loading. You can also account for surface finish factor, loading factor, size factor. The material description and the fatigue strength are shown when you select a single body. The fatigue check plot calculations are performed, and you are notified if your model is susceptible to fatigue failure. Now, a green icon right at the bottom of this dialog box indicates the model is safe and will not fail under repeated cycles of loading. All selected bodies appear blue in the graphics area. However, if you see a yellow icon as shown here, it alerts you that parts of the model could actually fail due to cyclic loading, and the regions of your model that are most susceptible to fatigue are shown in red. And so the program or this particular plot automatically alerts you to run a full-blown fatigue study to access the safety of your design in more detail. Now, another useful plot is called the results equation plot. Using this, you can create custom plots by using math functions to manipulate existing nodal and elemental results. For example, hydrostatic stress or max shear strain values are not something directly reported by SOLIDWORKS simulation, so it makes most sense to use a results equation plot to create these plots and extract the visual as well as the numerical data on custom outputs desired. In this example shown, a results equation plot has been created for the max shear strain. Now, this equation is simply a function of the elemental strain in xy directions and the shear in y direction on the yz plane. Now, SOLIDWORKS simulation calculates these values as a direct output, and so as a user, you can just combine them using the mathematical expression to get the custom output desired. So here's a plot of the max shear strain based on the results equation used. Now keep in mind that this plot works and behaves like any other default plot, so the options to manipulate and save these plots are not different at all. So here's the clamp model inside SOLIDWORKS. A nonlinear analysis has been performed on this particular geometry. Now to access the results equation, you can right mouse click on the results folder and choose the results equation. Now the equation editor pops up, and here you can select nodal values or element values to combine. And the type of functions supported are standard mathematical functions, any kind of stress or displacements for nodal values, and for element values you have access to those standard mathematical functions, stresses, and strains. So here's a plot of the equivalent strain. This is what it looks like. And here's a plot of the max shear strain. While working with linear or nonlinear dynamic studies, in addition to stress, displacement, and strain plots, you also have access to velocity and acceleration plots as shown. Note that the ones highlighted in red require a reference coordinate system as described earlier. Now, The response graph gives an XY plot of stress or displacement or velocity or acceleration versus time or frequency at predefined locations or at all nodes or at remote locations as well. Here are some examples of the response graph that you can get. The top one is acceleration in g versus time for a time history analysis, and the bottom one is acceleration versus frequency for a harmonic analysis, or for a random vibration analysis, this would be the PSD of acceleration versus frequency. The compare results is a very powerful tool to help display multiple result plots simultaneously in split windows. You can also plot and compare results between different simulation studies and across multiple SOLIDWORKS configurations. This option is best accessed through the SOLIDWORKS Simulation Command Manager as shown. After running your studies, you can display simultaneously in split windows up to 4 result plots. You can compare the results plots from the same study or across different studies. The simulation studies can be from the same or different configurations. Let's take a look. So here I have 4 frequency studies created, and the analysis has been run for all of these 4 studies. I'm going to go ahead and use the compare results and go ahead and select the option all studies in all configurations, and I'm going to compare the mode shape number 1 across these 4 studies. When I click OK, the program automatically splits the window into 4 viewports, comparing the results across those multiple studies from multiple configurations. So again, a very neat yet very powerful tool for being able to compare results across multiple design studies side by side. The frequency response graph in a frequency study allows to create plots of frequencies versus mode number, effective mass participation factor, and cumulative effective mass participation factor. The mode number plot just creates a line graph of resonant frequencies versus mode numbers. The cumulative effective mass participation factor creates a line graph that shows the cumulative effective mass participation factors for the global XYZ directions. Now, mass participation factors are important, as you know, in determining how many modes should be considered to capture adequately the dynamic response of the structure. Many codes require that the number of modes considered must contribute to a value of at least 80% of the system mass in the direction of excitation. The effective mass participation factor creates a bar graph that shows the effective mass participation factors for the global XYZ directions for each and every mode. Now, the effective mass participation factor represents the percentage of the system mass that participates in a particular mode. It provides a measure of the energy contained within each resonant mode. So a mode with a large effective mass participation factor is usually a significant contributor to the dynamic response of a system. Next, let's talk about being able to create a body from a deformed shape. So in SOLIDWORKS simulation, you can save the true deformed shape of a part or assembly resulting from running a static or a nonlinear static study. So in the example illustrated, the original shape and the deformed shapes are shown. Let's say the deformed shape needs to be exported as a new geometry for simulation or maybe for CFD or manufacturing purposes. So you can now save the deformed geometry as a new configuration or as a new part file. The end result is shown here, where the deformed shape, for example, is saved to the same SOLIDWORKS document in a new configuration. So using this at the assembly analysis level will result in a multi-body part. Also keep in mind that this feature works really well for solid meshed bodies only and is not supported for shell or beam meshed bodies. One great way of sharing and communicating simulation results for enhanced collaboration with clients or team members is to save the plots as eDrawings. So today you may be using eDrawings for parts and assemblies and drawings in SOLIDWORKS, but the good news is it works exactly the same way for simulation results. You have the option to save each plot separately into an eDrawings file or save all plots as shown here. I prefer to save all the plots into a single eDrawings file. That way it's much easier to share and collaborate the entire set of simulation results in a single shot with someone who may not have the tools. Also, since all the plots are now available, I can toggle back and forth between, let's say, the stress plot, displacement plot, factor safety plot inside eDrawings very easily. I can even turn off fixtures and loads plus superimpose the mesh as well on top of the contour plot. So this is really a very cool yet very powerful functionality or feature available to you inside SOLIDWORKS simulation. Well, that concludes this presentation. You can review this presentation as well as several other presentations as part of the Simulation Step Up series on the Simulation YouTube channel. I'll see you next time. Thanks and have a great day.